So I'd like to follow up on the little assignment that you did where you calculated the correlation coefficient. And so what I want to emphasize is a correlation coefficient is a number between -1 and 1 that indicates the strength of the linear relationship or how linear the relationship is between two variables. Now, for the remainder of the course, you're not responsible for knowing how to compute the correlation coefficient. You do need, however, to know how to interpret it and roughly guess a correlation coefficient from a scatter plot that you're given. So now, interpreting the correlation coefficient, if R is approximately equal to 1, there is a strong positive linear relationship between x and y, meaning that y increases as x increases. A correlation coefficient closer to 0 means that there is no linear relationship between x and y does not tend to increase or decrease as x increases. And a correlation coefficient of -1 indicates a strongly negative linear relationship between x and y, meaning that y decreases as x increases. So now we're going to take a look at some scatter plots, and I'm going to give you the values of R, and so you'll be able to judge based on the appearance of a scatter plot more or less what the correlation coefficient is. So if we have a correlation coefficient of 0, then the points plotted tend to be more in a circular pattern with no real trend, either positive or negative. If we have a correlation coefficient of 0.3, you start to see a slight upward trend, but it's not all that strong. It's more shaped like a football or a rugby ball, sloping upwards. Correlation coefficient of 0.7, now you start to see more of an upward trend here as x increases, y tends to increase, but it's not perfect. But you'll notice that the slope is getting flatter for the points, so that it is a little bit flatter than for when correlation coefficient was 0.3. Moving up to a correlation coefficient of 0.95, you can see that the points, the scatter plot, are tighter around a linear relationship, and so it's sloping upward and becoming very flat. Now, a correlation coefficient of 1 would mean that it's perfectly linear, and so that the points all lie on a straight line sloping upwards. Negative correlations, the same sort of similar idea based on the magnitude. So if we just consider the absolute value of the correlation coefficient, these are very similar. So here is correlation coefficient of -0.3, -0.7, -0.95, and -1, where in this case, all the points lie on a straight downwardly sloped line. Now, values with R with real data. So here's a rough guide as to how to interpret correlation coefficients that arise in real data. So values between 0 and 0.1. These have little or no relationship between x and y. So that knowing a subject's value of x gives you essentially no information on predicting the value or the measurement for y for that particular subject. For example, the correlation between income and shoe size among 30 to 39-year-old adult males is nearly 0, meaning you could have a high income, a small shoe size, or high income and a large shoe size. Moving along to values between 0.1 and 0.5, the relationship between x and y is weak, and so that subjects with higher x values do tend to have higher y values, but it's not a perfect predictor. Knowing x alone does not give you enough information to predict y precisely. You get an idea of whether it tends to be higher or not, but you can't make a perfect prediction based on this. So an example, the correlation between heights of fathers and sons is about 0.4, meaning that short fathers in some cases have tall sons and vice versa. So because of the mother's genetics being a part of it, it's not a perfect predictor when you're looking at the heights of fathers and sons. So the correlation coefficient is about 0.4. Fathers that are taller tend to have taller sons, but it's not an absolute. So now values between 0.5 and 0.9. So these X and Y are related to varying extent, to some extent. Again, subjects with higher X tend to have higher values of Y. And so knowing X allows you to predict with considerably greater accuracy than if you didn't know Y. So for example, the correlation between systolic blood pressure measurements taken twice in the same examination is about 0.6. So that means that they tend to be related. If you tend to have high blood pressure in the first reading, then you tend to have higher pressure in the second reading. And the correlation coefficient between students' scores on midterm and final exams tends to be about 0.7, meaning that on average, or if a student has a high mark on a midterm, they tend to have a high mark on the final exam, and vice versa. However, it's not an absolute. You're not guaranteed getting the same mark on both the midterm and the final exam, but it tends to be, if you do get in the mark, for example, a mark of 80 on the midterm, then typically you're between 75 and 85 on the final exam. So values close to 1. A value of approximately equal to 1 indicates that X and Y have a strong linear relationship. X and Y could be measuring exactly the same thing, although perhaps on different scales. As an example, the S&P 500 and the Dow Jones measure stock performance. They do this differently, but if you compare their averages, then they tend to be very close as far as their correlation coefficient, that when S&P has a high value, Dow Jones tend to have a high value as well, and vice versa. Also, if you take a look at temperature, the correlation between the measurement of temperature in Fahrenheit and the temperature in degrees Celsius is essentially 1. And that's because they're measuring the exact same thing, but in different scales. Now, note about the relationship. We have said that correlation coefficient between 0.1 and 0.5 indicates that X and Y are weakly related. However, in some fields, for example, sociology or behavioral sciences or psychology, a correlation coefficient of 0.3 or 0.4 might be called strong or even very strong in those situations. For example, suppose a developmental psychologist found a correlation between 0.4 and the level of internet usage and externalized behavior problems in a group of school children. This would be considered high or even very high because it is rare to find a risk factor that is correlated with behavior problems to such an extent. Meaning, some kids may have violent behavior when they play certain games, but others do not. It's not a perfect predictor, but if there is a correlation of 0.4, then it tends to indicate that this might be the case. So for the purposes of this course, we're going to say that values between 0.1 and 0.3 indicate a weak relationship. Between 0.3 and 0.7, the relationship is moderate. Between 0.7 and 0.9, we're going to say that the relationship is strong, and anything greater than 0.9 is considered to be extremely strong. But be aware that these adjectives mean different things to different researchers in different fields of study. So now regression and prediction. Correlation analysis makes no distinction between X and Y, so that if we reverse X and Y, the correlation coefficient doesn't change. So if we're measuring cholesterol and the body mass index, and then reverse so that we have the cholesterol level on the independent axis and body mass on the dependent axis, then we end up with the same correlation coefficient. So in this case, it doesn't make a prediction as to whether cholesterol affects body mass or body mass affects cholesterol. And later on, I'll talk a little bit about correlation and causation. There is correlation, but it does not imply causation. Their two variables might be related, have positive correlation, but there might be other factors that are the cause of the correlation. So a regression analysis, sometimes called linear regression analysis, is for predicting one variable from another. In regression, we must decide which variable will be the explanatory X variable, or the independent variable, and the response variable, or the dependent variable. The choice is usually motivated by whatever theory or hypothesis of causality, and I'm going to talk a little bit about that later on. And so the alleged cause is X, and the alleged effect is Y. So be aware that the ability to predict Y from X does not prove that a causal relationship exists if the data came from an observation study. And what regression does is it produces a straight line that estimates the average value of Y for any specific value of X. For example, if we've got this value, so this is approximately 32 for body mass index, we can make a prediction as to the cholesterol level for that particular individual. And so here it would be about 220. The equation regression line can be used to make predictions by interpolation, which is what I just did there, and extrapolation. Interpolation is estimating the values between the data points, and extrapolation is estimating values that are outside the range of the data. So for example, here, this would be interpolation, the one I just did, and extrapolation because we don't have a body mass index over 35. So here I've got a body mass index indicated for over 37 approximately, and using extrapolation, we're going to make a prediction that a person with a body mass index of 37 would have approximately 245 for the cholesterol level.